Welcome everybody to our Tutte Colloquium, Tutte Seminar. And it's my pleasure to introduce today's speaker. Today's speaker is Ricardo Fukasawa. He's in our own department here. And Ricardo got his PhD degree from Georgia Tech in 2008, if I get this right, working also with our own Bill Cook, who's not here, unfortunately. And then got a distinguished award at the IBM Special Fellowship Postdoctorate Award, and then came here. So, Ricardo, the floor is all yours.
Thank you, Henry. And it's a pleasure to be back here. It's been a while, I guess, since the last time I spoke at the Tutte Colloquium. Thank you all for coming. I apologize for the colors. I've just realized and been told that it's like maybe a little light, but hopefully that won't be too much of a problem and everybody can still read. So today I'm going to be talking about fast exact algorithms for combinatorial interdiction problems. I didn't say fast when I announced my abstract, but I thought it would be appropriate. And this is joint work with my PhD student, Noah Wenninger. Okay, this is a bit of a bold outline. I'm not sure if I'll have time to go through all of this, but I'll try to see if I can touch on most of those things. Talking about essentially knapsack interdiction, MST interdiction, and then some generalizations of it. Okay, so just to introduce sort of the basic concept in this problem. If you have like a basic integer program, and not just like, I guess, integer program, but like classical optimization problems, are problems of some form like this, right? You have some objectives, some constraints, and integrality constraints, right? One key assumption, not only of this, but of a lot of these optimization problems, is that there is a single decision maker that's controlling everything, right? It allows us to control whatever are the x variables. I can decide all of them. That's great. But it sometimes doesn't apply, right? So there are sometimes situations where this assumption doesn't really hold. For example, in adversarial settings where there are, for example, multiple and oftentimes competing decision makers, or when you're not allowed to coordinate efforts, right? So you really can't do all of this. You don't have a single decision maker that takes all of the decisions. Okay? So that lets people to start studying a slight generalization of that, where you have a bi-level integer program, where you have, for example, two decision makers. So the upper level decision maker controls the x variables, or sometimes called the leader, right? So I have some constraints on the x and y variables. And then the lower level, the follower, controls the y variables, right? And so if you forget about the bottom part, the top part is essentially just a regular IP, but now you have an extra constraint that y has to actually be a maximizer of this lower level IP, okay? That's why we have two levels. And the typical assumption is that what happens is that the first guy, the guy that controls x, acts first, right? It chooses x, and then given that x, y takes their own decision, okay? Optimizing the lower level integer program. So that's the setting for bi-level IP. So I'm typically going to refer to the upper level feasible region as this capital U. And I'm going to refer to this lower level feasible region that's dependent on the x decisions as L of x. Okay, so that also goes along the lines of x decides first, and then y has some restricted set of decisions, L, depending on what x decided.
So that also includes the U, right? Because y, that U is also constraining y.
Yes, yeah. It's not going to be in our case, but yes. So that's the generic idea of bilevel IP. Just to give you sort of a very brief flavor how this thing starts getting hard, if you look at the problem of bilevel linear program, you could do something like this, right? You could have some continuous knapsack constraint here on the 0, 1 hypercube, right? So these are continuous. I could have chosen anything here. But what do you have? I say that y is a maximizer of this guy, right? But then I have a high cost or a high negative cost of getting any y to be positive. So what I would typically want is that all of these y's, they are 0, but they're only 0 if x is either 0 or 1, right? So essentially, I'm modeling here binary knapsack, which is an NP-hard problem, by using a bilevel linear program, right? So this gives you an idea where this hardness starts coming from, because I'm imposing this extra constraint that y has to be this maximizer of this lower level problem. I can start now encoding some harder constraints by using sort of easier subproblems on this bilevel setting. Okay? So it's not too hard to see that this is an NP-hard problem, but it's like it wasn't even known until very recently that this was a problem in NP. So this is just to say that there's several questions on these bilevel settings that have still not been addressed. Okay, so what we're going to be looking at is a special class of bilevel optimization problems, particularly bilevel integer programs, which are called interdiction problems. What's the main idea is that the upper level decision maker can choose to block or interdict some of the decisions that the lower level can take. Okay? And it's a special form of that bilevel IP because the lower level has its own optimization problem to solve there. And the only thing that the upper level wants to do is it wants to hurt as much as possible the lower level guy. Okay? So it wants to make lower level guy's life as bad as possible. That's the objective, right? So it's a special case because now it's like these conflicting, it's directly opposite to each other. The lower level guy wants to maximize P transpose Y. The upper level guy wants to minimize that. And like it made me think of like my son, which some of you know, when he was younger, he used to say that his goal in life was to make his sister's life as miserable as possible. So it's the annoying sibling problem that sort of reminds me of that, right? So that's the thing, right? The objective is just to hurt the other person as much as possible. Okay. Good, so like this has several applications, right? And people have used these types of problems and studied. For example, the lower level decision maker could be somebody trying to smuggle drugs from one place to the other, right? So they typically have some type of flow problem that they want, and the upper level can try to break down some of these arcs subject to some budget constraint, right? So that's some application of this type of interdiction problem. Other people have studied these types of problems, for example, in the context of trying to stop spread of hospital infections. So again, trying to think that like hospital infections are in some way trying to go from one place to the other, and then how do you try to sort of block these stages of contagion so that you minimize total hospital infection, right? Also, like other people more recently have studied other applications in terms of like trying to design some resilient network, right? So I'm trying to sort of allocate customers to some capacitated facilities, and the leader tries to interdict those facilities with the goal of trying to find the resilience of our system to attacks, right? So you can see where these start having a lot of sort of applications in these situations, okay? So this is just, again, to motivate why do we care about these types of problems. Okay, so what was the goal, right? What do we want and what do I want to talk about in this talk? That's the title, Fast Exact Algorithms for Combinatorial or some Combinatorial Interdiction Problems. What do I mean by fast? Typically, the thing is that solving these problems, it's really hard to do. Typically, the general purpose solvers are really slow. What I mean by fast is not worst case runtime. The worst case runtime is going to be terrible. What I'm interested in is empirical computational time. So how much time does it take for me to run in instances of interest, okay? Exact, because I want to compute the actual optimal solution to this problem. I'm not interested in approximate solutions. I really want the true optimal solution to the problem. And which interdiction problem? So we chose to study sort of, we wanted to study very classical fundamental problems in this setting, right? We didn't want to stay like some very fringe problem that didn't seem to have too much interest. We wanted to study very, very fundamental problems. So that's our goal, and that's what I'm going to try to present to you. Okay, and then overall, that's what we wanted to try to do in this work, is can we push what's the state of the art in terms of solution time by designing some problem-specific algorithms. And then can we get some ideas in these problem-specific settings to start getting some more generic framework to work, okay? So that was the sort of overall arching theme that we started with this work, and that's what I'm going to try to present to you. Okay, so the first of these problems that we've studied is called the knapsack interdiction problem. So here is the problem. We're given, just like in knapsack, a set of items from 1 to n. Each item has 3 quantities associated, an upper weight, a lower weight, and a profit. So it's the upper weight, the lower weight, and a profit. And there are upper and lower knapsack capacities, and we're going to assume all of these are integer, okay? So that's the statement of the problem. If you look at the lower level guy, all it's doing is it's solving a regular knapsack problem on the items. The only thing is it's only allowed to use items for which xi is 0, right? So in other words, the upper level guy can choose some of the items. If I choose some of the items on the upper level, they are forbidden on the lower level. Okay? So that's the interdiction setting. Both have knapsack constraints. Okay, this is actually a sigma 2p complete problem, which is, if you know what it is, great. If you don't know, it's like a level harder than NP hard. There is a paper that claims to have a PDAS, and I think it's been out on archive. I'm not sure if it's published in any other place. So there is no pseudo-polynomial time algorithm for it. There is, so sigma 2p complete also says that there is no polynomial size, even IP formulation for the problem. And these are sort of a brief history of the exact algorithms that are there for the problem. It was proposed in 2011, and then people have been evolving and solving larger and larger problems. These are all roughly on the same scale, and then this was sort of the best work that appeared in 2018 that solved instances with at most 500 items. And all of these are MIP-based. All of these rely on formulating the problem as some mixed integer program, not a polynomial sized, but a general mixed integer program, and then starting adding cuts to it, okay? The stars just are to say that these are sort of approaches that weren't derived specifically for this problem. They were for more generic problems. They were just tested on these types of problems. Okay, so that was sort of the state of the art when we were starting to look at this problem. Did I go forward? Oh, that's fine. Yeah. So we decided to try to do our own approach to solve this problem that wasn't based on mixed integer programming, with essentially the idea that, like knapsack, that's not what you do. If you're doing knapsack, you don't solve it as an IP, you solve it by some more combinatorial algorithm, right? So I wanted to first start by sort of presenting this very simple branching rule, which is sort of a simplification. It's not exactly what needs to be done in this problem, but for the purposes of presenting, it's okay. So I'm going to assume that the variables are ordered in this sort of greedy order for the lower level. And I'm going to assume that the branches are always going to be consistent. So branching at depth I will always be done on variable xi plus 1, right? So the first branch, I'm going to say, do I pick x1 equals 0 or do I pick x1 equals 1, and so on. And then ith branch, do I pick xi equals 0, do I pick xi equals 1, okay? It's a very simple branching scheme. It just essentially is enumerating all possible choices, right, of the upper level decision maker. Okay, so that's fine. That's obviously not going to work. What we need is a good way to bound these things, and that's what we attempted, and that's what helped us tremendously on this problem, right? But what is the key thing? The key thing is that any branch and bound node is identified by essentially a subset x of the items 1 through I minus 1, right? Because I branch always on this order, that have been picked up to this level of branching, right? So this is which items did I pick already to interdict. So I can identify essentially all branch and bound nodes by the subset x and the level of branching y. Okay? And now I need to construct a lower bound on that node. I need to figure out how far I am from the optimal solution of that node. So how am I going to do that? We're going to do three things. We're going to solve a lower level knapsack on these items from essentially the first I minus 1 items, except the ones that I've already interdicted. And then I'm going to compute a lower bound for the binary knapsack restricted to the items that are coming afterwards, right? So I'm splitting between what I've already branched on and what I'm going to branch on in the future. And now I want to combine these two things into a lower bound for all of the descendants. Okay, so that's just to set up some notation. So I'm going to say that kx of c is what? Is the solution essentially of the lower level knapsack. When I take out the interdicted items x and I give the lower level knapsack a total capacity of c. Okay? So I give the lower level knapsack this total budget c and I'm interdicting items x, that's kx of c. Okay? So what is this lower level knapsack on these items? It's just k of x and everything else, right? I'm excluding x and I'm excluding all the items that come after. And I'm giving it some capacity c. What is this lower bound for the binary knapsack problem restricted to the items that are coming later? I'm going to set this lower bound as this quantity. Right? It's going to be some omega of I, Cu and Cl, which are going to be the upper level capacity and the lower level capacity. It has to be a lower bound out of all possible knapsacks right? Where I'm forbidding all the I minus 1 items, right? So I'm restricted to items I through n, given some lower level capacity CL, right? And that I also am allowed to restrict some of the other items that are coming afterwards, given that I have an upper level capacity of CU. Okay? So that's what this omega quantity represents. So omega I CU CL is the best, a lower bound on the best that I could do on the remaining nodes, given that I have remaining capacity of CU on the upper level and remaining capacity of CL in the lower level. Okay? And I want to combine these two things into a lower bound for all of the descendants of that node. Okay? So I want this to be a lower bound for this guy, which are the descendants of that node, right? So it's anybody that's feasible for the bilevel knapsack and that match what I've already interdicted, right, up to this point. Okay. So, and then we can actually say that this is the way you combine is you can just sum these two things. One thing that I wanted to mention is that I didn't need to have this defined, I guess, in terms of this I, CU, and CL. I could have just defined as some omega of X and I, right? But one thing that's important computationally is that I want to be able to bound this node with just a limited amount of information from that node X, okay? Sort of jumping a bit ahead of myself, it's because what I don't want is I don't want to, for every possible subset of X, I don't want to recompute this quantity, right? So I compute this quantity once and in advance, and then I can use it for several branch and bound nodes, so I can save a lot of computational time with that. Okay. But then the proof that if I sum these two things, I get a valid lower bound is really easy, right? So what do? I'm saying, well, I've already interdicted the items X from 1 through I minus 1, and then from items I through N, I'm going to interdict something else, some X prime, right? So it's clear that what is this saying? This is saying what? That's for all pre-allocations of the capacity C, right? So this is saying I'm splitting the lower level capacity by allocating C to these first items and the remaining capacity to everything that comes after, right? So if I pre-allocate, I cannot do better than don't doing any pre-allocation, right? I allow everybody to use the whole capacity, right? So this inequality follows trivially. Well, therefore, if I minimize overall X prime, I also have that inequality. Yes?
Just wondering, so for this lower bound, are you using the true ILP or are you using LP realization?
For this lower bound, I'm using the true optimal value of the IP. Yeah. For this to hold, right? So as long as I have this, okay? This is a valid way to derive that, and with that, I essentially derive that inequality because this is exactly the right-hand side, and omega is a lower bound on exactly that. Okay? So it's a very easy proof. Okay, good. But now, it assumes that I have this quantity, right? So that's a lower bound on that, okay? So the question is, how do I obtain this quantity, right? I want something that's going to be less than or equal to all possible solutions to this lower level knapsack, right? Assuming that I've already interdicted some items with upper level capacity CU. Okay. So what's the idea? How do we try to do this? We're going to use this idea, WWGD, which is what would greedy do? Okay, so this is what we're doing. We're saying the following. I've already branched, right? I've gone through a bunch of decisions, what I have interdicted, up to item I plus 1, up to item I, right? And then what am I going to do? I can either sort of interdict this, this item, right, which is the blue guy, which means that, well, if I interdicted this guy, that means that I'm left with an upper level capacity because I've used that guy, right? And then I use the lower bound for the following item. And the lower level guy has no option, so it won't actually use any of the capacity, right? Or I didn't interdict that guy, in which case, since I have this ordering, right, of the greedy ordering for the lower level, it means that the lower level guy will pick that guy up, right? So I didn't use any upper level capacity, but the lower level guy picked that item, so it's going to use that amount of capacity, of the lower level capacity, and then it's going to get a reward because it picked that item, okay? So what did I do? I assumed that the lower level is actually using some very well-known strategy for me, right? It's using the fact that it's using greedy to solve the lower level problem, okay? And if you do that, well, what is it saying? Well, it's saying it's using the greedy, and the greedy is less than the value of the actual knapsack, because that's what you do. The greedy is just a feasible solution for the knapsack problem. Therefore, you can have that this is smaller than this total amount, which is like optimal, so it could just go higher than that. Right? So that's roughly the idea how you would get such a lower bound. Okay? So that's like the first idea that we had that allowed us to say, well, okay, I can do this and I can get some lower bound based on that. Yes?
I mean, doesn't this grow exponentially as I increases? Because each time you get a new I, you have to do 2 new things, or no?
No, you'll do this because what you'll do is you'll do this like in a dynamic programming fashion, right? So just like you would do in knapsack, that's essentially like a knapsack type recursion, except knapsack you would have this and then just one extra guy, which is how much of the knapsack consumption you have, right? This is essentially like a knapsack recursion. Now you do this knapsack recursion on just 2 different knapsacks. Okay, so it's the capacity gets multiplied by each other, but you do this dynamic programming type recursion. So it doesn't blow up, well, it could blow up exponentially, but it doesn't blow up if the capacities are not too large, essentially. Okay, so that's the idea. We're trying to sort of do something like a knapsack type DP here. We couldn't do that to get an optimal solution, but we can do that to get bounds. Okay? Yeah, and then it becomes a lot cheaper to do. Are we good? Okay, good. So that's one thing that worked for us in that problem. But we can actually improve on that a little bit, because what did we assume? We are going to assume in the greedy, what did we say? We say that, well, the follower is always going to take that item if it's possible, but it may not be the best possible strategy for the follower to do that, right? So the follower is actually optimizing the knapsack, so it may not actually get that greedy solution. So we improved that a little bit by allowing the follower to do a different choice, right? So again, if I interdict that item, then there is nothing else to be done because the follower doesn't have that item available. But now if I do not interdict, that item is available. So now I allow the follower to do nothing, right? So it doesn't lose any of the lower level capacity, or I allow the follower to pick that item, okay? So they can do now one of the 2 things, whichever one is better, okay? And again, you can still compute this in a dynamic programming type recursion, but it will get you a stronger bound, right? Because the follower is following a slightly better strategy. Okay? And then again, you can prove that this is again still the lower bound that you need, and therefore everything else follows. That's essentially basically the main ideas of what we needed to do, and then there's lots of other like things, but I think these are sort of the main key things that were done. One thing that I think comes out nicely, and it's going to sort of come up later, is that one way to interpret this is the following. If you now look at this idea that we're allowing the leader to do one thing and then the follower also does something that reacts to that, it looks like they're taking turns, right? The leader does something and then the follower can act differently. And so it becomes like a two-end stage game where each stage is essentially very simple, right? So in a picture, this is what was going on. The original problem goes like this. In the first round, the leader selects a whole subset of the items that are available to interdict and interdicts the red guys, right? Whatever is left for the follower to pick, and then they can pick some blue items, right? That's the original problem. What we did in our relaxation was to modify this sort of game in the way that they play alternative, right? So the leader is just going to look at item 1 first, and maybe it decides, well, I'm not going to pick that, then the follower can pick it, right? And then after that, well, the leader is going to decide on the next item. It's not going to pick again, but the follower doesn't pick it either, right? And then it continues like that. The leader picks the next item, so it's not available. There's nothing to do, and the game goes on like that, right? So we transform this like 2-round game into this 2N round game where each round is essentially a lot simpler, right? It's just a very single binary decision, okay? And that's going to play a role a little bit later, so that's why I wanted to highlight this at this point. Okay, based on this is what we got. These were the results of the previous best in the literature. The main things here is, okay, number of times you get the optimal solution. These are the number of times this was the best approach. So you can see that we beat them in a huge majority. And the running times, they drop significantly, sometimes from 900 seconds to 1 second, right? So it's orders of magnitude faster, okay? So just by doing some very nice ideas, but simple ideas, we're able to sort of reduce a lot computational time, and we've achieved our goal to improve the state of the art for this problem. Okay, any questions? Well, yeah.
How do you know you have the optimal solution? For example, how do you know you're stable in the perturbations, in the small perturbations?
What do you mean stable under small perturbations? I have the optimal solution for the instance that's given.
Well, how do you know you have the optimal solution? Because maybe small perturbation in the data changes the problem dramatically.
I mean, I'm assuming that all the data is integer, so I'm getting like integer numbers. There's not going to be any like floating point errors or anything.
But that doesn't, well, maybe talk later. That doesn't mean it's stable. Still could mean that an integer change can make a drastic solution.
Sure, I mean, so a small change could change completely the optimal solution. I agree. But for the set of numbers that were given, it's the optimal for that set of numbers. If you give me a slightly different number, yes, it could vary completely. Yes.
Okay.
Yeah. Okay, good. So let's move on now to the next problem, right, which is the minimum spanning tree interdiction problem. So in that setting, we're given, again, our graph. We have edge weights, which we assume they're in this decreasing order. They're all non-negative, and edge capacities, again, all integer. And then there's an knapsack capacity. So it's exactly the same setting. The upper level still has a knapsack constraint. Now, the only thing is that the lower level solves a minimum spanning tree problem, and now we're trying to maximize the cost of that minimum spanning tree. Okay, it appeared as like some variations, like the K most vital edges when all these weights are 1. And there are some IP formulations. Swami with Andre had derived a 4 approximation for this that improves on this approximation by Rico. So one of the things that we realized is that, okay, we can try to do what was sort of successful, right? we had this very successful approach for knapsack interdiction. We can try to maybe do something similar, and that's what we tried on this problem. You can look at this interdiction problem, right? We still have an upper level knapsack constraint. It's essentially the same, except that we have a weird objective function, right? I choose some subset of items that satisfies a knapsack, and then I just have some weird function z of x. And in this case, z of x is just solving the minimum spanning tree on the graph, removing the edges in x. Okay. So what can we do? One way that we can tackle this is the following. Let's suppose that I'm going to define this notation x less than or equal to I to be all the elements of x that have index less than or equal to I, right? And similar with strictly less, right? So if you define delta I of x as this, the difference between z of x less than or equal to I and z x strictly less than I, you could think of this as how does the value of the minimum spanning tree changes when I was interdicting only items up to I minus 1, and now I'm allowing to interdict item I as well, right? So what's the value of that change? If you write it in that way, I can rewrite this equivalently as that, right? This is just essentially going to be a telescopic sum. This is going to be z of x, and then terms cancel out. So this is just z of empty set, which is just the minimum spanning tree of the graph. And now this starts looking a little bit more like knapsack, because now we have sort of each one of the items I sort of in a sum independent of each other, right? So this starts looking a little bit better. Okay. So what did we do? Well, let's try to derive an upper bound for this, right? So again, the previous time I derived an upper bound that was based just on this item I that I was considering, and then some remaining capacity that was left, right? That's what we did in the knapsack. So that's what we're going to try to do again. So it's again, like I said, it's like a discrete derivative. We're going to say we're going to try to do this GIR, which is an upper bound on all of these delta IX terms for every x such that I don't use that much capacity to interdict, right? So R is the remaining capacity. It means I've already used C minus R only, okay? So that's the same thing that I said last when I was talking about the knapsack, is that I'm trying to derive these bounds that don't depend on x, they just depend on sort of this quantity, this amount of capacity that I've used already. Okay, and then with that, I can just essentially define this, again, knapsack type dp, right, where I just define this f, which is just I either pick this item, don't pick this item, or I've picked this item, and then I can pay or I can get that increase on the cost of the minimum spanning tree, right? It's not hard to see that that essentially will give us an upper bound. You can just relate this, right? MST of G is just this guy, right? Z of epsilon. And then what you get here is upper bounded by F1 of C, okay? So that's how we get an upper bound on that, right? The key thing is how do I derive this quantity Gi of R, right? Okay, so in the in the knapsack problem, we had this WWGD approach. We're going to say essentially the same, except that now I know how to actually do the optimal minimum spanning tree. So I'm going to try to find out what would the Kruskal's algorithm do. Okay? Good. So what am I trying to figure out? I'm trying to figure out is the value of the replacement edge. Did I say this somewhere here? Yeah. Okay, never mind. So I'm trying to find an upper bound on this difference here. There is an easy case, right? So let's look at this graph, right? I'm assuming that everything on the black is items that came before edge I. Edge I is this red edge here, okay? So that's, yeah, the black edges are everything before. The red edge is UV, is what I'm trying to consider right now. Well, what happens if I compute the minimum cut in this graph without the red edge, and the minimum cut is large, right? What does it mean? It means that I cannot disconnect U and V using at most C minus R weight, right? Well, because of that, if I can't disconnect this, for example, if I have this capacity that I'm allowed to use for the edges, 1 through I minus 1, it's 7, right? I can't disconnect these two edges with that much capacity, right? Therefore, if I come to this edge and I'm running Kruskal, these two vertices are already connected, right? So that edge is never going to be in the minimum spanning tree in any case, right? So that means that this edge is not in the minimum spanning tree, so these two things are equal, right? Whatever I had done before, it doesn't matter because edge I is not going to be in there anyway, so these two things are equal, so therefore those guys are 0, right? So I can immediately set those to 0. So this also says that, well, let's try to see what happens if that doesn't hold. If that minimum spanning tree, if I forbid the items up to item I minus 1, if it doesn't contain that edge, then by the same argument, the minimum spanning tree doesn't change. So this is again 0, right? So what I try to find is what is going to be the cost of replacing the edge. So the edge EI should be in the minimum spanning tree. If I take that off, what's going to be the cost to replace that edge, okay? So that's what we're going to try to do. Okay, and I'm going to sort of do sort of a proof by picture here. So I'm going to say again, notation on the picture is the black items came first. The item that I'm considering is the red guy. The blue guys are coming later on, right? And then I'm going to highlight some of the edges that I've interdicted out of the black edges. Okay? So let's look at this, right? I'm looking at this guy. I'm looking at the next edge that came. Is that possibly a replacement edge for the red edge? And it has to be valid for any choice of x less than I, right? Or any choice of interdiction set, right? I'm assuming all edges have unit capacity, just to be simple, and that I can essentially interdict at most 2 of them, okay? So what do? I try to find the minimum cut on the edges that came before taking off the red edge, and I put an infinite cost on the blue edges, okay? What do I get? What would Kruskal do here? Well, Kruskal would pick this guy, that guy, that guy, that guy, that guy, that guy, and that guy. Right? So if I take this edge off, this blue edge definitely wouldn't replace that, right? Because it's going to be connected. So that's not a replacement edge, right? So I need to move on to the next edge. So is it possible that this is now a replacement edge, right? So what I'm going to do again is compute the minimum cost on that graph with the blue edges having cost infinity and having removed the red edge, right? So that will give me this interdiction set here in purple. So what would Kruskal do then? Well, Kruskal would do this, this and that, and then this, this and that. Right? It would pick these edges, and then it would pick the red edge. But then afterward, it would also pick this next blue edge here, right? So that edge is already in that minimum spanning tree. So if I take this off, that blue edge is not a replacement still. Okay? So I'm taking off this guy. This blue edge was already in the minimum spanning tree, right? So Kruskal would also pick this guy. So this is not a replacement edge. Neither this nor that guy is a replacement edge. Okay? So I'm going to do that again. A next edge comes in. Again, I'm going to compute the minimum cost, the minimum cut with those guys. Now, what am I observing here? What's happening? The minimum cut has value 3, and I only have a budget of 2 for that, right? So now I cannot interdict all of them, so maybe I can interdict these two, and then what would Crusoe do? It will do this, this, and that, and then we'll pick this, this, and that, right? And in that case, what would happen? It would have added this guy, and then it would have added this guy, and then it wouldn't add this, right? Because if I have the red edge, all of these vertices here are connected already, right? But then if I take this red edge off, then I all of a sudden would add the blue edge, right? So that is a replacement edge, okay? And I could sort of keep doing these examples, right? At any time now, if I have this, one of these three will be the replacement edge, right? That's essentially the idea. I can do this again, but I'm not going to do it in the interest of time. Essentially, the first time that this minimum cut becomes bigger than the remaining capacity, I've gotten that the replacement edge is either this or one of the edges that came before, okay? So it's good that I know how the algorithm that solved the lower level is going to act, because now I can exploit that, okay? And that's what justifies sort of our notion that we have here, right? Again, if the minimum cut is not that big, I'm going to pick the first time the minimum UV cut becomes bigger than the capacity. That's going to be the cost of my replacement edge. Okay, so that's again a very simple idea, and that's what's implemented. And with this, we compared against several of the other approaches. Again, this is the best from our literature. This is sort of the 2 different variants, and you can see again huge gains in terms of running time, right? From 6,000 seconds to 1 second. That's what we get, and this is in a different set of instances. Again, 2,000 seconds to 11 seconds in the bigger instances, 7,000 to 60, right? So a huge improvement, okay? Just by doing these types of things. Okay, I'm going to skip that, and I'm going to sort of use sort of the very few remaining minutes to start talking about this sort of generalization that we're trying to look at. So we looked at these 2 problems. Great, we got extremely good results, right? We beat previous approaches by orders of magnitude. Now, let's try to extract from this what is it that we can use, that we can generalize, that maybe can be applied to other settings, right? And that's what was the attempt that we're trying to do right now, actually. So that's what this question is. Is there a common structure that I can identify that can be used to other types of interdiction problems? So the approach that we're trying to do is exactly this idea of transforming these 2 rounds, right, that I highlighted before. That was sort of the original knapsack. I choose one set of items, and then I go to the next one, and then they choose the second set of items, and it's done, into this 2n set of rounds. Each one of them is very simple, right? So we try to generalize that, and I'm not going to have time to do a lot of the details there, right? But that's what we sort of try to start into abstract, right? We have some first level constraints there, some first level problem, x in F1. F1 is the feasible region, and the second round does xy in F2 is a feasible region for the second guy. That's the standard bi-level setting. And so we sort of reframe that as some arbitrary number of rounds. And then I'm not going to go over this notation because it's going to take a while. I'm just going to sort of say, what is it that we did, right? We did, I think I can sort of speak to this just as a broad outline. The operations that we can do are the following, right? We can restrict, essentially, the actions of one of the guys, right? Which is what we did in some sense, on the knapsack, we assume, for example, that the follower is going to always follow the greedy, right? Or the follower is always going to do Crucible and things like that. So we're restricting what are the possibilities that one of the players is going to do. So we can have that operation. We can do is, if we have some of these rounds, we can exchange the order of them. We can merge two rounds, right? So if we have two consecutive rounds, we can say that, well, put them together. Or do the other way around. If you have a round, we split them. And all of the rest is sort of a combination or something like that. But with that, essentially, we can derive, with these operations, we can rederive everything that we had done so far, right? The knapsack problem, the MST interdiction, we can derive all of that using just these types of operations, okay? So that's great. We said, well, good, we can generalize it. What does that do for us? Does that help us in any way? And it turns out that the answer is yes. So this is, again, too much notation, which I won't have time to do. But that's essentially what I was just saying, that this essentially gives us what we had done before. And we can actually do this if we apply this to this maximum weight matching interdiction problem, where again, the lower level problem is just solving maximum weight matching. And then by just using these simple operations, we can derive three different bounds. One is a bit too hard to solve, so we didn't even do that. But there's two other bounds that are essentially just doing some of these operations on this game. And then we can, with that, we can derive a branch and bound scheme again, and we can sort of derive an approach to solving these interdiction problems. And we compare that against some basic reformulation of the problem that's sort of the standard approach when you have an LP formulation for the lower level. You can dualize some things and you get a MIP formulation out of it. So again, if you do the standard MIP formulation type of thing, you get these types of results. If you get the bounds that we obtain just by doing this very generic thing, you get better results, right? This is the number of instances solved. We solve more instances, the higher these sizes start getting with less time overall. Okay, so that's essentially what I wanted to talk about. It was a bit rushed, and I knew that it was a bit sort of ambitious to try to go through all of that. But the key ideas was this, right? So what we did, we're trying to exploit strong bounds by assuming some lower level strategies, right? That's what we did in the knapsack. This idea of using 2n rounds of a simple game, which essentially led to these game theory type framework. One of the key things computationally is that we can get these DP-based lower bounds, so we can compute this relatively efficient. Overall, this is a sort of important topic. People are getting more and more interested in solving these in practice. It's very challenging computationally. It's very challenging theoretically as well. We sort of achieved what we wanted to exploit structure and derive good combinatorial algorithms for it. We showed essentially, I think, that even sigma 2p hards of significant size instances can be solved. And now we're working again on further developing this sort of game theory type of framework, studying other interdiction problems. We're trying to extend maybe to more general settings where you don't assume just that you have an knapsack constraint on the upper bound. And we have some vague ideas on using decision diagrams for that. And maybe we'll use also some primal dual algorithms on the lower level. And that's it. Thank you.
Okay. Thank you, Ricardo. We definitely have time for some questions.
So in the first example, the knapsack example, your lower bound had two terms, but already the first term, the capital K, that's NP hard, right? Unless you make some assumption so that you can use DP. Isn't that NP hard, that just to get that first term?
So it is NP hard not to, so it's NP hard to solve the problem, but like to get the bounds that we get, it's, well, I guess it's still NP hard, but you can use a dynamic programming table for it, right? So if the capacities are not too big, then we're okay. We're still on a pseudo polynomial world.
In view of the game theoretic framework that you proposed at the end, I was wondering if, so round one was when the leader interdicts some variables, right? And I was wondering if at round two, we can at least decide if the follower can force a win. Just deciding in polynomial time if they can force a win.
I mean, it's not really, I guess, it's hard to define it as a win because it's not like a binary thing where you either win or lose. It's just how far you derive the objective, right? So how much you can affect the objective function of the other. So I'm not entirely sure.
But I read somewhere that the framework uses zero-sum bi-level optimization, right?
Yes.
So it's a zero-sum, so there is some sort of win and lose.
I mean, I guess yeah, what do you mean by a win or a lose is by how much you win or lose, I guess, right?
Yeah.
So yeah, I mean, it depends a bit, like how far do you want to get from maybe a baseline? Yeah, I don't think it's going to be that easy to do something like that.
Okay, thank you.
Okay, well, thank you again, Ricardo.